This video is going to replace the lab lecture for Lab 1, the Friedel-Crafts Alkylation reaction that we're going to do this week. So, the Friedel-Crafts alkylation is a member of the class of reactions that we call an electrophilic aromatic substitution. So, in an electrophilic aromatic substitution, we have, excuse me while I play with my pens, we have an electrophile. And as we said before, an electrophile is something that has usually an empty atomic orbital, or an atomic orbital that we can make empty. And then we need a nucleophile, something that has electrons. In this case, the pi bond of a benzene ring system. So those electrons then leave the bond and enter that empty orbital. That creates a carbocation, and in this case we call that carbocation an alpha complex. As with a number of carbocations, that alpha complex can act as a Bronsted-Lowry acid if we have a Bronsted-Lowry base around. If we deprotonate that, the electrons in the carbon-hydrogen bond of the carbon alpha to the carbocation, those electrons can move over to recreate the pi bond. It recreates the aromatic system. That aromatic system is unusually stable, and so we tend to get that recreation in these products. Now, because these aromatic systems are unusually stable, it takes a strong electrophile, right? The electrophile must be strong in order to get an effective reaction, and then we tend to recreate that system in the end. Okay, now, in the classic version of the Friedel-Crafts alkylation, we use a carbocation as our electrophile. But the problem with carbocations, we know from other reactions involving carbocations, is that carbocations are inherently unstable. That means they are difficult to form. That means when they do form, they tend to be there in very low concentrations. So one challenge is, how do we generate high enough concentrations of the carbocation to be effective reacting with that stable aromatic system? Well, what we will do is we will use another Lewis acid to promote carbocation formation. And our standard Lewis acid in the classic version of the Friedel-Crafts alkylation is aluminum chloride. So we will start with an alkyl halide, right, where we have a halide leaving group, and we will have aluminum chloride present to make that leaving group even more effective. So, the aluminum chloride is a Lewis acid. It has an empty orbital. An unshared pair of electrons on the chlorine can interact with that empty orbital to create a new complex. And we see that formation of the new complex, where we have the chlorine now complexed with the aluminum. This aluminum now has an octet, so that is a stable complex. The chlorine is now positively charged. This makes the chlorine an even better leaving group, meaning it's even more likely to leave than usual, so we have a better chance of creating our carbocation product. So here we see the complex. We see the electrons going with the chlorine in a classic leaving group pattern. And you get the carbocation product, which will be our electrophile for the Friedel-Crafts alkylation. So, our carbocation acts as electrophile. The electrons from the pi bond enter that empty orbital in the carbocation. We create the alpha complex where we have a carbocation, this hydrogen adjacent to it. That can be a Bronsted-Lowry acid. And so something acts as a base. In this case, it is probably our negative aluminum tetrachloride anion, where the chlorine pulls on the hydrogen ion. That tends to make the chlorine leave. The electrons, right, as chlorine pulls on the hydrogen ion, these electrons tend to fall back into the aromatic system, but that protonated chlorine then is likely to leave, and you end up with our alkylated product, right? There's our alkylated product, hydrogen chloride, and we regenerate our aluminum chloride, so it's acting, in this case, as a true catalyst. So, if that works so efficiently, the question then becomes, why don't we just use this reaction in our laboratory, right? Why can't we just use the reaction as we just laid it out in our laboratory? Well, there are some problems. One, aluminum chloride is kind of nasty. If you go back, it's one of the things I remember Dr. Brooker, when he used to talk about this reaction, would say, instead of, if you're doing this reaction, let your lab partner add the aluminum chloride, and you leave the room, right? Aluminum chloride is very reactive. One of the problems is it is strongly hygroscopic. If there's any water around, not just liquid water, but water vapor, that is any humidity in the room, aluminum chloride will try to react with it. And when aluminum chloride reacts with water, you make aluminum hydroxide, which is a solid, but you make 3 moles of hydrochloric acid, and the reaction is strongly exothermic. And so it releases a lot of heat. So you've got the release of hydrogen chloride gas. It is a very strong Lewis acid, right? It reacts with many Lewis bases. And that reaction is strongly exothermic with most Lewis bases. So that combination means it's very hard to work with. And so we would like to avoid that kind of chemical, if at all possible, in the undergraduate organic laboratory. So we need another way of doing this reaction. So how will we generate carbocations without using aluminum chloride? Well, we've done that in the past. So we will take advantage of other reactions that generate carbocations. Now, these reactions will by nature be less efficient than using aluminum chloride. So one of the things we'll do is we will use the most stable carbocations possible. That is, tertiary carbocations, so that we can get the greatest yield possible. But even with that, our yield will be low compared to what we would get if we were using aluminum chloride with an alkyl halide. So we're going to add groups to the aromatic system to make it more reactive so that we can get an effective reaction even with a lower concentration of carbocations than we would get in a typical Friedel-Crafts Alkylation. So, we're going to use a tertiary alcohol as our source for generating carbocations. So, we'll do what we've done in the past. We'll use sulfuric acid. We will protonate our tertiary alcohol. Right? And as our tertiary alcohol will act as a Bronsted-Lowry base. Sulfuric acid will act as a Bronsted-Lowry acid. And we will get an alkyl oxonium ion. Right? In this case, a tertiary butyl oxonium ion. That tertiary butyl oxonium ion then can undergo heterolytic dissociation. That is, the leaving group can leave and take the electrons in that bond with it, leaving our carbocation with water as the leaving group. Now, as we've said, this is going to be less efficient than if we were using an alkyl halide and aluminum chloride. So that means the concentration of our tertiary butyl carbocation is going to be much lower than it would be if we were using an alkyl halide and aluminum chloride. Okay? So if we were using just benzene, this reaction would be too slow for us to get anything done. So somehow we have to increase the reactivity of our aromatic system in order to get this to work. So, if you look at what we just did, it parallels what we did in the classic Friedel-Crafts alkylation. Right? If we look, we have something that is a potential leaving group that we would like to make better. And so we have that interact with a Lewis acid, and that creates a complex, which creates a situation where now this whole thing becomes our leaving group. And this is a better leaving group than that was by itself. Right? In the same way, when we protonate this, the hydrogen ion is playing the role of Lewis acid in the same way that the aluminum chloride did. And this creates a complex where this, that is our original leaving group plus the Lewis acid, in this case water, is a better leaving group than what we had on there in the first place. So even though these two reactions look very different, what we're accomplishing in each case is very similar. And then once we have our carbocation, we can focus on the aromatic system. One of the things we said is we need to increase the reactivity of the aromatic system. And we're going to increase the reactivity of the aromatic system by adding methoxy groups. We're going to use 1,4-dimethoxybenzene instead of benzene by itself. 1,4-dimethoxybenzene is more reactive in these kinds of reactions, in electrophilic aromatic substitutions, than is benzene by itself. So we react and we get an alpha complex that would look something like that. Now, part of the reactivity, part of the increase in reactivity is that if we go back to this alpha complex that we just created, we have a carbocation here, that is a carbon with only 6 electrons, adjacent to an oxygen that has unshared pairs of electrons. If we go back to our rules of writing Lewis structures, whenever we have an atom with unshared pairs of electrons, adjacent to an atom deficient in electrons, those electrons can be shared to create a pi bond, which means that this positive charge is shared. Some of the times the positive charge is there, some of the time the positive charge is there. And that extra resonance form tends to stabilize the overall reaction intermediate. And that tends to make the 1,4-dimethoxybenzene more reactive than benzene is by itself. Then, once we have that, our alpha complex can act as a Bronsted-Lowry acid. Probably the best base around is a molecule of the alcohol that is unprotonated. So a molecule of the tertiary butyl alcohol acts as the Bronsted-Lowry base. The alpha complex acts as a Bronsted-Lowry acid. The electrons in the carbon-hydrogen bond fall into the ring to recreate the aromatic system, and that step of the reaction is complete. And then, this ring is activated. As a matter of fact, alkyl groups also make the ring more active, because as we remember, alkyl groups, through the inductive effect, tend to donate electron density, so they tend to increase the electron density in general in the ring, and thereby make them more reactive. And so the combination of our methoxy groups and our tertiary butyl group all tend to make the ring more reactive. So going through this reaction again to add the second tertiary butyl group is even easier and occurs even faster than the first one. And we end up with our product, the 1,4, 1,4 ditertiary butyl 2,5-dimethoxy benzene. So, that outlines the mechanism. Notes on the procedure. The reaction of the sulfuric acid with the tertiary butyl alcohol is strongly exothermic. We saw that back in our labs in the first semester. And so we're going to cool both our alcohol mixture, our alcohol reaction mixture, and the sulfuric acid in an ice bath before combining them. You'll put the sulfuric acid into a separatory funnel, and you will use that separatory funnel as an addition funnel, and you will slowly add the sulfuric acid to the reaction mixture dropwise from that separatory funnel. Once the reaction is complete, you will use a combination of crushed ice and water to cool the reaction mixture and to drive the solid product out of solution. Note, you'll wash the crystals with methanol, but then you will recrystallize your product using a minimum volume of ethanol. So, this is a good lab. We can get it done. The reaction goes in a fairly straightforward way. We should get a decent amount of product. If you have any questions, please let me know as quickly as possible. Thank you.